next speaker is Benjamin Basso from Université. Title of the talk is non-graphic
Okay, thank you. So, first I'd like to thank the organizer to give me an opportunity to talk in such a famous place. So, it's another talk about the Cusp, anomalous dimension, and okay, based on the work done in collaboration with Grigory Korczynski and Jan Kotansky. So this is the item I would like to cover. So first, what is the Cusp anomalous dimension and where does it appear? Then how to compute the Cusp. So I will try to sketch the better ansatz approach to calculate the Cusp anomalous dimension, and its strong coupling expansion from the BES equation, and the test of ADS CFT of this result. So what is the Cusp anomalous dimension? The Cusp anomalous dimension has been defined by Polyakov in the 1980s, and it governs the renormalization of a Wilson loop evaluated over a closed Euclidean contour with a cusp. So as for the case of Wilson operator, that are composite operators taken at the same point, such a cusp in the contour produce new kind of singularities, and to this singularity is associated anomalous dimension. And this anomalous dimension depends on the coupling constant of the gauge theory, and also on the angle there, theta. Fortunate property of the Cusp anomalous dimension is that it controls infrared asymptotics of scattering amplitude in generic gauge theories, and yeah.
Your microphone a bit over
Sorry.
this side. I was just asking Steve what.
Yeah. I will try.
Should be a bit better. Or stick it onto the thread there, maybe.
It's better? Yeah. Okay, sorry. So the Cusp controls infrared asymptotics, and it appears when someone does computation. The contour, integration contour, is defined by the particle momenta considered, and in this case, the Cusp is related to the scattering angle between the particle momenta in Minkowski space. So there, the angle now is measure hyperbolic angle, and in the limit with very large angle, a new object can be defined, and this is the Cusp we are considering in this talk. This object is present in many places in gauge theory, like infrared singularities, as has been discussed yesterday, and logarithmic scaling of anomalous dimension. This is a subject I will now present. So we work in planar n equal 4, super Young mills, and in the planar limit with the Taft coupling constant defined in this way with NC goes to infinity. The weak coupling expansion of the Cusp is known up to 4 loop, and the 3 loop result has been obtained by Kotikov, Lipatov, Onichenko, Velidzanin, starting from explicit QCD computation and making use of the transcendentality principle to select the good contribution to n equal 4 in n equal 4. Then to computation there as permitted to obtain the for loop result presented here.
I don't want to be picky, but I mean, it's just, I think it's always, I mean, most people don't know, I think, that what Cajasso et al. In the end did, they got an extremely precise numerical value of
on this number.
They don't really, I mean, for the moment, nobody has evaluated the Bern et al. Integrals analytically, which would be very interesting. So it's known to 0.001%,
exactly,
whether it agrees. But strictly speaking, this precise analytic form has not yet been derived from the.
You're true. This has been computed analytically, and the coefficient in front of zeta 3 has been fitted.
They just get a total number for the whole thing, the sum of the phi and the theta, and they just get some very precise number, but it's not. It's not yet complete.
Okay, it's not exact.
No, if you, of course, I personally have no doubt that it's correct, but it's just, it makes sense.
Okay, so this expression for the Cusp at small coupling fulfills the Kotikov-Lipatov maximal transcendentality principle. It means that there is equality between the order, the number of loop of the computation and the power of pi there, or in fact the indices of the zeta function. The strong coupling expansion is also known from ADS-CFT correspondence. This has been computed by Gubser, Klebanov, Polyakov, and Kruczynski. And the free log 2 over 2 pi has been computed by Frolov, Zeitling, and also by Kastel, Christiansen, starting from the better ansatz. And in this case, the cusp corresponds to the semi-classical expansion of the energy of a folding string spinning in ADS3 times S1. So 1 year ago, conjecture was put forward about the form of the loop cusp anomalous dimension, and this is the problem we try to solve, and a lot has been done just after the equation has been proposed, and it appears to be a very difficult problem, as I have seen the several groups that work on the problem. So the anomalous dimension, the Wilson operator were considered. There are second trace operators built from L scalars and n Lycan derivatives. There are two quantum numbers, the twist, that is given by the number of scalars, and the Lorentz spin that is given by the number of Lycan derivatives. The scaling dimension of the Wilson operator can be identified as a spectrum of the dilatation operator, and is given by a canonical part independent of the couplings constant and an anomalous part. The anomalous part depends on the two quantum numbers, the twist and the Lorentz spin. So there is many anomalous dimension for a given twist and Lorentz spin. But all of them in the large spin limit are bounded by 2 times the cusp, the logarithm, and the twist times the cusp, and also the logarithm. So this is now and a particularly interesting branch of anomalous dimension is the minimal one that has universal scaling. By this we mean that in the large n limit there is no dependence on the twist, as you may see, and as you may see also the cusp is present and governs this logarithmic scaling. So now, how to compute the cusp? So to compute the cusp, we have this tool that is integrability, and integrability. So a short story of integrability. Integrability has been discovered for gauge theory in QCD by the works of Lipatov, Then Heisenberg spin chain has been identified, and also in the sector of anomalous dimension, this was for Ridgey effective theory, and later integrability in the sector of anomalous dimension we are considering has been discovered in n equal 4 and QCD and n equal 4 and extended to Wilson to maximal range to all Wilson operator, and we hope to all loops in planar n equal 4. So what does mean integrability? Integrability means that we can solve the spectral problem with bet-ansatz. So there is a one loop example, everybody know there, and to each anomalous dimension we have a set of bet roots and equations that must be satisfied by these bet roots, and another one that is a cyclicity condition, zero momentum condition that I had no place to write, and the relation to the anomalous dimension. This problem is hard to solve for generic twist, and since we are interested in the Cusp anomalous dimension, we are going to take the large spin limit. In this large spin limit, one can introduce distribution density of bet roots and replace the algebraic problem by integral equation. In this case, for example, in this one loop example, the bet roots condense at the origin, and that produce a logarithmic scaling. And so if you know how to compute this, then you can, making use of this relation, compute the Cusp anomalous dimension. So this is the idea. At one loop is it's not difficult. And in order to compute the Cusp at any loops and maybe to go to the strong coupling limit to compare with string theory, it has been necessary to have an all-loop description of the anomalous dimension. And so it's just a sketch of the story, how to go from the one loop to this proposal. And the set of reference is not complete. There is also reference have already put above. So people start to explore and try to understand integrable structure in planar n equal 4 at higher loops. People also did a lot of work on the string side of the IDS-CFT correspondence to understand integrable structure and to compare with the gauge 1. People have understood the necessity and presence of dressing phase. So in different paper, and then a crossing symmetry has been proposed to be a property of this dressing phase, and at the end a proposal has been made. So the whole picture converged to this all-loop asymptotic bet-ansatz. It's in this case for SL2 twist operator, and the all-loop asymptotic anomalous dimension that follows. Okay, so the meaning of asymptotic, as it has been discussed this morning, is because of wrapping effect, and I will not discuss this. So now these all-loop asymptotic bet-ansatz are very difficult to solve, and we are going, as in the one-loop example, to the large spin continuum limit, and this is known as the BES equation. So the first equation is ES equation. It was it's the same equation without the dressing phase, and then people had this dressing phase and write down this formula. So there we have the distribution density of roots or to be more precise, it is not the, it is a fluctuating part when we separate the one loop result from the rest, the remaining. And there is a kernel. So the kernel is a bit complicated with Basso function, and okay, and the relation to the Cusp anomaly is quite simple. So we would like to solve this equation, and it's particularly in the strong coupling limit, but it's very hard. But we can have a look at the weak coupling first. This has been done. And in this case, it is possible to solve this equation by iteration. And it is straightforward to obtain the perturbative expansion of the Cusp anomalous dimension up to higher order. So what can be said about this weak coupling expansion? First, it reproduces the known for loop result. It verifies the Kotikov-Lipatov maximal transcendentality principle to all loop. And interestingly enough, the numerical analysis of the coefficient indicates that the weak coupling expansion is convergent. So now we would like to do the same for the strong coupling. And okay, so now I switch to the strong coupling. And first, the numerical approach. So what one can do in order to obtain a numerical solution to the BES equation is to expand the solution over the Basso, so and then truncate the series with boundary condition. If you do that, you obtain a finite dimensional matrix equation that you can solve numerically, and so compute the Cusp anomaly numerically and fit the strong coupling expansion. So the results are stable, so it's good. And we have a remarkable agreement with the string theory result, since this is a Gapser-Klebanov-Polyakov result, and this is follow-up settling 3 log 2 over pi. And this, for the moment, is mystery. Alors, it is also possible to look at the analytical approach, and in this case we have the same setup as before, but we do not truncate the Basso series, and we work with the infinite dimensional matrices or continuous BES problem. We look for an expansion in 1 over G, and we try to solve the BES equation perturbatively, order by order, in 1 over G, if possible. So these people try to do that, and it's possible up to 1 over G square, but the solution is not unique. The solution is defined up to 0 mod. The ambiguity at the leading order can be fixed by imposing a constraint that inspired by the numerical solution, and this is the result. And from this, you can compute the Cusp and observe the agreement with string theory. Then you can go to next to leading order and try to solve, and we will find the same ambiguity, and so also we can fit, if you want, the coefficient from the numerics and observe the agreement with the 3 log 2 over pi of the string theory, but it raises the question how to go beyond this 1 over G square expansion, and how to fix the 0 mod coefficient to be predictive and to eventually to compare with string theory. So in order to do that, we first have to simplify a bit BES equation, And so I propose to decompose the solution into two new objects where plus and minus are associated with the parity, so even and odd, and also introduce this new object with the same signification for the plus and the minus. So the claim is that the BES equation is equivalent to this infinite set of equations, and as you may observe, the G dependence disappears from the kernel, and now is inside this function. This system of equation has many solutions, and in order to pick up the good one, we have to impose the analytical properties of that produces the BES solution. So the good analytical properties are the fact that the small function there, gamma, are entire function of t that translate because of this map into a meromorphic function condition for the big gamma with pole located there. So you observe that the G dependence is on the boundary condition or analytical condition of the solution and not in the system of equation. And there is also one more solution that since this function are entire function, we can decompose them over the Basso function, and we also require the coefficient of this expansion to be given by this integral. In fact, this is equivalent to the fact that this development is convergent to the small gamma with a dominated argument, in order just to commute the sum and the integrals. And nicely enough, there is only one such solution. So if we are able to find this solution, we find the solution of the BES equation. The relation to the cusp is the following, it's just this. And there I put a kind of sum rules formula that relate the cusp to some integral. There you observe that this object is positive, and so the cusp is positive, as it must. And and also this is this kind of argument, quadratic argument, that allow someone to prove unicity of the solution. It relies only on the fact that if you multiply on both sides there by the coefficient gamma and then sum, we will observe that this term there pick up the cusp, and the remaining produce this object. And so if this term is absent, so if we are looking at homogeneous solution, so at another solution that differ by an homogeneous solution, you will obtain that under the condition this must be equal to 0, and since this is positive, this is 0. So we are happy, and now we try to solve this simplified BES equation. So the idea is there is a plot of the Basso coefficient, and the problem with this expansion in 1 over g is that the expansion is not uniform in n, and in fact this 1 over g expansion works fine near n order 1, but it fails to describe this decreasing at large n. And in order okay, this is the main idea to construct the solution. So first we construct an asymptotic solution and parameterize the contribution of infinite number of zero modes. So as you will see, there is an infinite number of constants that will appear, and then we have to select to impose quantization condition to select what must be the values of this constant in order to reproduce the BES solution. This we can do, in fact, because we learn from numerics that the solution has remarkable scaling behavior that will allow to sue two asymptotic expression, and so to control control the large n in some sense, as we will see. The large n expansion of the solution in order to select the good one. So this is a result. So in the 1 over g expansion development of the solution, so you write this object you develop over the Basso, and this is our result. The coefficient of this expansion expand as follows, with coefficient there that admit an expansion. So we look for a solution with coefficient that admits a development in 1 over g. There we have an infinite number of zero mode, and so infinite number of coefficients that we have to determine. These objects are known and have explicit expression, and the Cusp anomalous dimension, or its large G expansion, is expressed in terms of this coefficient as follows. So now we have to find a way to determine all these coefficients, and we have to go in some sense to the large n behavior of the solution in order to select the good one. And what we did, we examined the asymptotic behavior of the coefficient. So there is a coefficient for big gamma, but we can undo the change of the mapping and go to the coefficient of little gamma. That is the solution we want to constrain. And we look at the asymptotic behavior in this double scaling limit for n large and g large, and this ratio fixed. So the numerics, from the numerics, we learn that this object has a remarkable behavior in this limit. And where you admit expansion in integer positive power of x, and knows about all the coefficients I have introduced before. So we start with this parametrization. We impose double scaling limit plus some analytical properties on the solution, and we obtain quantization condition. This quantization condition just are constrained on the coefficient that must be fulfilled in order to select the good solution. So it's an example of the 1 over g, the next to leading, in fact, quantization condition, and its solution. And if you solve this, so you compute C plus, C minus from this relation. Everything is known on this side, so we have a system of equation. And and if you compute the Cusp anomalous dimension, you will find the free log 2 over 2 pi in agreement with Saclay-Frolov computation. So it means that it is possible to compute the strong coupling expansion from BES equation. And this free log 2 over 2 pi has been obtained also in different ways by Belitsky and, as I've said before, also Castel and Chris Jensen.
Excuse me.
So, yeah.
One question. So from your previous transparency, like what people was doing wrong, me for instance, was to expand in G for fixed n. So you should have expanded for fixed x.
What people did, in fact, they expand in G. What you did is you expand in G, and so in fact what you obtain is this expansion cut at p equal 2.
Yes, but then you should have fixed n but x.
And then we have to take both the limit n large and g large, and this limit you cannot cannot reach this limit if you have not the infinite power of subleading solution. So then it's just a question of time to solve the quantization condition order by order, and obtain this result. So this is our prediction from BES equation for the cusp. So these are the coefficients that appear. So we have the Catalan constant, we have zeta 3, we have Dirichlet zeta function. The special function that enters in the cusp, and there the free log 2 over 2 pi has disappear because it is absorbed in the shifting of the coupling constant. So what can we say about this development? First of all, it is in agreement with the numerical values obtained in the numerical approach I have presented before. Then it fulfills a kind of maximal transcendentality principle. And the difference with the weak coupling is that you have to change zeta with even indices into beta with even indices and keep zeta with odd indices intact. And another remark we can make is that the free log2 dependent term inside the cusp can be absorbed by shifting the constant. It means that if you don't do that, you will obtain a lot of C1, C1 square, C1 4, and so on.
Any idea what that means?
In fact, I'm not sure, but I learned that such phenomena are usual in semi-classical quantization. That the
analog of when imagine you have an harmonic escalator, you want to write quasi-classically. So you start with harmonic escalator, then you write like a dequantization condition. The dequantization condition always you have integral pdx equal to pi integer plus 1/2. So the 1/2 comes from quadratic fluctuation. So this 1/2
analog is kind of a vacuum energy of something.
Again?
The kind of a vacuum
Yes,
energy
yes,
of
but
something.
this 3 log2 it comes out when you take quadratic fluctuation. It was a classical solution. So just quadratic fluctations around the vacuum.
But why do you add it to the coupling constant?
No, but imagine when you write quadratic condition, in classical quadratic condition, quantum mechanical system along harmonic escalators, you always will have n plus 1/2, right? And this 1/2 came about when you take into account first quantum correction, right? So once you have quadratic condition, which depends not on my n, but n plus 1/2, you know a priori that the final expression will not depend on n, from n plus 1/2.
It seems that point that n plays the role of coupling.
Yes.
Yeah.
And 1/2 is quantum correction to the classical analysis.
So it may be an explanation. So now the IDS-CFT correspondence and the test. So the cusp has two interpretations on the string theory side. And the perturbative string theory prediction is the following. So there it's a classical, there's a one loop and the two loop. And recently, Raban, Tirziut-Seitling, and Raban-Seitling has succeeded in computing the two loop correction. And as you observe, it is consistent with the result we obtained. So in some sense, it's IDS-CFT works fine for this observable two loop accuracy. Then what can be said about the higher orders? So it may be difficult to test this term, and but what we can see, what we can learn, is that all the expansion except the first one are negative, and the expansion coefficient grow factorially at large orders with their factorial. It means that the strong coupling expansion of the cusp anomalous dimension is not convergent and is only asymptotic, and is not Borel summable because of the absence of flipping sign. And one may ask the question, what does it mean? What does it mean on the string theory side, such a behavior for the 1/G expansion? So, well, you can do this trick, Borel improved expansion, and in order to learn what is called non-perturbative ambiguity to the cusp. And if you do that, you will observe that the cusp has intrinsic ambiguity, non-perturbative ambiguity, that scale as follows. And on the string theory side, recently, Alday and Maldacena has identified a non-perturbative scale in string theory. In their paper, they describe the scale as follows. So they have massless excitation of the string sigma model related to the non-critical O6 part, and with a UV cutoff fixed by the mass of the other fermion and boson excitation. This O6 sigma model, this non-critical O6 sigma model, is asymptotically free and develop a mass gap. And this is the expression for the mass gap. And if you take the result well known for the one loop and two loop beta function of this O6 sigma model, and plug into the mass scale, the dynamical scale of the O6 sigma model, you will obtain perfect agreement with the non-perturbative ambiguities identified starting the BES result. So I don't know if it's not a proof, it's just it's just the fact that we have the same scale, the same non-perturbative scale that has been observed in two ways and that agrees. So maybe we have to think more about that. So now I would like to conclude. So what we learn is that the BES equation can be solved analytically at weak and strong coupling. At weak coupling, the Cusp anomalous dimension is given by a convergent series in G square, and at strong coupling, the Cusp anomalous dimension is only given by an asymptotic series that suffers from non-perturbative ambiguities related to its non-Borel summability. This non-perturbative correction may be governed by the dynamical infrared scale of the O6 sigma model. And okay, a perspective is to quantize, to have a quantitative description of this non-perturbative correction that is still missing, and if possible, the exact solution to BES equation. This maybe we will have. Okay, I don't know. Thank you very much.
Well, maybe I should ask Fernando this, but why do you think it goes as m? Why should the Cusp go anomalous dimension go as m squared on this O6 model, not say m?
I think because you can interpret the Cusp anomalous dimension as an energy density, and usually the energy densities receive corrections of the form m squared.
Yeah, explain that.
Why is an energy density?
Yeah.
Well, like in the computation we did at least, it was just like an open string, and the density of that infinite open string was the Cusp anomalous dimension. Yeah, I can explain how the computation went, but
More questions?
In double scaling, you have m minus 1/4.
Yeah.
Do you need this 1/4?
Okay. In fact, you can quantize. You can obtain the quantization condition without doing this shift of m. But with this shift of m, we obtain an expansion only in power of 1/g. Whereas if you don't shift this term, you will obtain an expansion in 1/square root of g. But it's not necessary to quantize. If you want, you can do the quantization program without using this. But
double scaling limit, we somehow trace back to what is its origin, like some property of the dressing factor or something.
This.
could you repeat the question?
Can one trace back this double scaling limit back into the equations? So does it reflect some property of the dressing factor, for example, the dressing kernel?
I don't know because the scaling limit is related to the behavior of the coefficient and the dependence on n of the coefficient. And I don't know how is it related to some properties of the distribution density of roots, or but
basically, basically, if you look for this formula, if what Fernando asked, if you look for this, just could it previous time? So if you look for the series of a p, right, and you just put fixed p, and then you look how this coefficient scales for large k, then you scale k power p. So each term of the series for large k and for large j, it blows up. And therefore, you have to say something how all the terms in the series are organized. For example, take exponential function, exponential minus x, and for x to infinity. The function goes to 0, but each term blows up. So therefore, if you knew the behavior of function infinity is growing exponentially fast, and you knew first few terms of the expansion, then it will be rather strong constraints on the particular form of the power terms. And here, what you're saying is saying exactly the same. You have this series, each term of which blows up. And then it requires that the whole series, for large values of this scaling variable, should decrease. And this information turned out to be sufficient to fix all those coefficients.
I think tomorrow we have a similar formula obtained in the rapidity space, and there you see that in the regime where near the singularities of the kernel, you have the different scaling, so the series you have to reorganize the series, and the way that the G's are put in this, and that's exactly ensures that you have a finite, not blowing up functions in this region. And I think this is also related to the observation by Maldacena and Swanson that in that particular region, which is called near flat space region in the terminology, basically you have to use all the orders of the DES addressing phase in order to get information about the first order in 1 over G. So somehow this is the way you can understand this formula.
And this double scaling limit is not trivial property of the equation. Basically, if you didn't know that it exists, you would never get it there.
Or if you have some analytical intuition about.
Okay, but the way, as Benjamin said, the way how we got around this, we just looked for the numerical solution, and then we just immediately found, looking at the numerical structure of the expressions, that it's there. And this was the key point for concern.
Questions?